Hello guys, in the previous video I have explained the theory part of constant satisfaction problem. So let me just recap it. So what is constant satisfaction problem? Constant satisfaction is problem is nothing but is a set of variables. It is a domain of it is a set of domains. For each set of variable there should be a particular domain, and we should have a set of constants for each variable. So then later we have described it in a mathematical rotation. Then we have find what is C of I. C of I is nothing but the set of constraints. The set of constraints is defined with the two parameters, that is scope and relation. Scope is nothing but the participation of each variable in the constraints, and what is relation? Relationship is nothing but defining the value for a variable. So that is the relation. What we have to the main name of constant satisfaction problem is that for each and every variable there should be certain value, and that value has to be satisfied by the entire world. So that is what the main name. So we have seen one basic example of a student. What are the variables here? Uniform, shoes, belt, books are the variables. And what is domain? Domain is class, section, department. And what are his constraints? Constraints are nothing but you should be on time to the college, you should complete all the assignments, you have to give the examination to promote to the higher level. So these are some of the constant satisfaction problem for a student. So then later we have dealt with the finite constant satisfaction problem. So in that we have seen when a module is given to us, so what are the basic tasks we have to do in that. So first we have to check whether it is a model or not. Then we have to find a model. But then we have to check that it is model is suitable for our constraints or not. Then we have to find the number of models are satisfying. After that we have to check the best model, and for that best model we have to check for the some statements sold to all the model or not. Then we have, so from the entire observation we came to know that the CFS solution, constant satisfaction problem solution, is always consistent and always it will be complete assignment. So now let us deal with the examples. So what are the examples? Main examples are: first one, graph coloring. Second one, sudoku. Third one, it is crypto arithmetic, right? Crypto arithmetic puzzles. So I will explain for each and every example. I will give a solvation part. So fourth one is nothing but the constant satisfaction using backtracking of graph coloring. COLOURING. So these are some of the examples of constant satisfaction problem. So I will now explain graph coloring, sudoku, constant satisfaction this crypto arithmetic puzzles, and CFS using backtracking with respect to graph coloring. Now I will explain these four examples. So let us first deal with the graph coloring. So graph coloring is nothing but coloring the graphs such that the adjacent regions should not have the same color, or the adjacent nodes should not have the same color. So first one, graph coloring. So let me take an example. So I have already explained you graph coloring in my ISN videos. You can, if you want in depth, you can go there and watch my videos. Now I will explain only the graph coloring with respect to CSP, that is constant satisfaction problem. So let me take a graph. Consider this as a graph. So A, B, C, D, E, F. So this is the graph given, and in solving the constant satisfaction problem, so in the question itself they will be giving us the constraints, and we have to write what are the variables, what are the domains. So they may also in some cases they will also give, and we have to find the solution as well as the variables for a given set. In this question they have provided us with the domain. So domain we have to use only the red color, red, green and blue colors. And what is the constraint? Constraints is nothing but the rules. So what is the rule in graph coloring? That no two adjacent regions should have the same color. So that is the constraint, that is adjacent adjacent regions must have different colors. So this is the domain and these are the constraints they have provided to us. Now we have to find the solutions of finding the variable, finding the domain, find the constraints, and also we have to find the solution for the entire graph. So let me note down the solution. So first one, what is that? First one we have to calculate the variables. Then we have to calculate the domain. So the domain is already provided, so there is no need to calculate. So then we have to find the constraint is already provided. Now we have to find the solution. So there are two parameters we need to find. That is, one is the variables and another one is the solution. So let me note. So what are the variables? Variables is nothing but the set of the regions, that is the nodes. So what are the nodes here? A, B, C, D, E, F. So these are the variables they have provided. So what is the domain they have provided to us? So domain is nothing but we have to use only the colors red, green and blue colors we have to use. So then what is the constraint they have provided? Constraint that adjacent regions must have different color. FFERENT, different colors. So now let us find the solution. So how do we find the solution? For example, we have, let's take a color, red color here. So let me draw the graph here. So this is the graph they have provided. A part, B part, and C is mixed with D part, E part, F part. Okay. So this is the graph they have given to us. So what we have to do, we have to color this. For example, let us start with the red. So for the A region, let me give red. So solution for A, I have provided with red. So B, what is the B color? So here red is present. So for the red color, for the A section, what are the adjacent nodes? B and C are the adjacent. So for B and C, we should not provide the red color. So we have to use the another alternative color. So for B, I will be choosing green color, GREN. So for here, green color, I have to GREN, green color. So what is now we have to check this one. So what is this part? This part is nothing but the C part, that is C. So C is adjacent to A as well as the adjacent to B. So what is adjacent of A? It is shaded with red color, and what is adjacent of B? It is shaded with green color. Now we have to shade the C part with different color. So let me take first C. So first C will be, what is the color left? Blue. So let me take blue color. Okay. So blue color. So next one, what is that? We have to take for the D. So here what we have taken? We have taken the blue color. So blue is adjacent to D and B. So without green and blue, we have to shade with the D with the different color. So what is the color left with us? Nothing but the D. So we have to check that each for the adjacent, there are different parts. So D is not combined with any of the red shaded part region, right? So D is provided with red color. Okay. So now let's move on to another one, that is E part. So for E, what color we have to use? So you see here. So E is adjacent to red, and E is. So for E, we have to use, instead of blue and instead of red as well as the blue, because it is touching to blue also, right? So here it is a gap in that. So E is attached. So E is attached to C. So there is a gap in this. So for the E section, it is adjacent to B region as well as the red region. So we have to use another color, that is the green color, green one. So what is the left node left with us? So we have chosen green. So for the F, what color we have to shade? So F is adjacent to green and also adjacent to blue. So what is the color left with us? It is the only color left with us is the red color. So for F, we will be giving red color. So this is how we'll be doing in a graph coloring. So we have to check for each region that there must be have a different colors. so there must should be have a different color. This is the example of graph coloring. So let us move to the another example, that is Sudoku. So Sudoku is a matrix representation of 9 into 3 into 3. So let me write 1 2. So this is a 9 box column, 9 into, so for each column there will be 3 rows and 3 columns, that is 3 rows and 3 columns. So what we have to do in Sudoku is it is a game such that, so it will be having a inbuilt numbers 2, 4, and we have to use only the numbers from 1 to 9 such that the entire box will be filled. For example, 1 2 3 4 5 6 7. So this is how we will be filling each and every row and column, and we have to check that in each and every row there should be no repetition of each no repetition of the value. For example, in this row, so we have already used 4 5 7, right? So we should not use 4 5 7 in the column wise or in the row wise anywhere. So that is one of the constraint of Sudoku, and Sudoku is the best example of constraint satisfaction problem, because it has so many constraints that every column should not have every column or row should not have the same color, as well as that it is a 9 into 3 cross 3 matrix. So user definitely will be getting confused, so where to place the value. So this is one of the example of constraint satisfaction problem. So let us move to the another one, that is crypto arithmetic puzzles. So what is crypto arithmetic puzzles? Crypto arithmetic puzzles are nothing but it is nothing but the mathematical representation where instead of numbers we will be placing letters. For example, when you solve the logical reasoning, so A will be considered as 1, or in case A will be considered as 2. For example, A and B is considered as 2, and so on to Z will be considered 26. So whereas in some of the cases A is considered as 2 and B is equal to 4, and so on, Z will be considered as 52. So there are some of the examples that what we'll be doing cryptographic puzzles. It is a mathematical representation where instead of values we'll be dealing with the letters, and then later we'll be solving what are them. So let me take one example, that is, so let me take 2 TWO2 2 plus TW 2 plus 2. So what is 2 plus 2? It is 4, FOUR. Sorry, FOUR. So when we add these two terms, we will be getting 4 FOUR. So in crypto arithmetic puzzle, how we will be solving is that, so let me show solvation. So how did we solve? So see, 0 plus 0, it's O plus O will be resulting to R, will be getting a result of R. So in case if R produce any carry value, so we have to give carry to the 10th place, that is 10 into carry to the W. Then after that we have to calculate this carry plus W which results to U. So in case U also produce a carry, we have to take the carry to the, so here carry is went there, and here we have to place the carry here. So you have to also take the carry, that is 10 positions of the carry into T plus T which results to O. After that, if O also produce carry, we have to give it to the F1. So this is how crypto arithmetic puzzles mainly deal with. So let me write the steps, how it is, what are the constraints and what are the steps, what is the process on all those. So first step, what we have done, we have added 0 plus 0 which results to R, which produces R. And also what is done, if in case it is have a carry, it will be having a carry of, that is the 10th place into, let us take the carry as C10. So here C10 is the carry part. So after this is the first step. So after the second step, what we have to do, we have to solve the carry, as well as the we have to add the carry, this W and this W to produce the U value. So C10 plus W which results to U, plus in case U also produce carry, we have to take to the 10th positions of the this term. So let us multiply 10 positions with respect to, so we have considered C10. So let me take it is 300 because it is 100 positions. So C100. So this is another carry. So let us move to the third step, that is C. Now we have to add the C100 position T and T which will be producing O. So C100 plus T plus W which results to O plus, sorry, it is O only, O plus what we have to do in case if this O also generates carry, we have to give to the 10th positions, 10 positions into, we have to take the carry, it is 1000 positions, right? So let us take C1000. So now we have to add the C1000 to produce the F. Only it has C1000, right? C1000 which results to F. So this is a basic theory of our crypto arithmetic puzzles. Or in case you can also do like this. What if A is equal to 4 and B is equal to 4, 8, C is equal to question mark, D is equal to, well, 16. So find C. So they will be giving like this. So what is the C value? So it is the A is equal to 4, A is equal to 4, B is equal to 8, C is equal to question mark, and D is equal to 16. You can see that there is a clear that it is the nothing but the 4 multiples. So 4, 8. So what will be having here? So it will be definitely having a 12 and D is equal to 16. So this is how we will be finding in a crypto arithmetic puzzles. So in place of numbers they will be giving us letters. So based on the letters we have to formulate it. So crypto arithmetic puzzle is a big concept. So later I will be explaining the each and every step of crypto arithmetic puzzle. So for any small notation of in constant satisfaction problem, just remember this is one of the example. So let me take the another example, the last example, that is constant satisfaction problem using backtracking. Constant satisfaction problem using backtracking with respect to graph coloring. With respect to graph coloring. So let me take an example. So consider this as a graph. So 1, 2, 3, 4. So what is backtracking? Backtracking is nothing but it is a recursive process where if any node or if any statement doesn't obey the rules, we have to go to the previous step and we have to check it is satisfy the given set of problems or not. For example, if any nodes of that branch satisfy that, we have to enumerate to those steps. So that is what backtracking. So next video will be next video is all about backtracking itself. So the later I will explain what is backtracking and what is applications and what are the examples, all those things. So for now we will be dealing with the graph coloring. So now with respect to constant satisfaction problem we have to do. So what is the variables? So here variables are 1, 2, 3, 4. 1, 2, 3, 4. So what is the domain they have provided? As domain we have to use only the 3 colors, that is red, green and blue color we have to use. And what is the constraint? Constraint is that if constraints are nothing but if one has red color, one should not have the same color as the same colors to the 2 and same colors to the 4. If 4 has one color, so 1 should not have the same color as 4 and 2 should not have the same color of 4 and 3 should not have the same color of 4. So like that is nothing but the adjacent nodes should have different colors. So this is the constraint of graph coloring. So let us try to find the solution. So solution is that, so we are using backtracking, right? So let me take a table notation. So there are 4 vertices, right? 1, 2, 3, 4. So this is x 1, 2, 3, 4. So what is the variable? First variable, what is the variable? 2, 3, 4. So let me take x down. 1, 2, 3. and 4. So this is the matrix representation. Now we have to find the graph coloring using a backtracking technique. So for one, so what are the colors they have provided to us? Red, green, blue. So for the 0 iteration, so every variable can be defined with the each and every letter. So let me take for one. So red can be given, green can be given, and blue can be given. For red can be given, blue can be given, and green can also given. For third, red can be given, green also blue. And for 4, red, green, blue can be given. For the 0 iteration, that we didn't even plot the graph. So later for the first iteration, I will be giving, for the first node I will be giving the red color. So what will happen if we give the red color? So for the first one, I have placed with the red color. So one has the neighboring nodes as 2 and 4. So for 2 and 4, we have to not use the red color, so remaining colors can be used. So in place of 2, we have to remove red. That if we remove red, what are the variables, what are the colors left with 2? G and B. And for 2 is adjacent for 1 and 4 is adjacent for 1, right? So for 4 also, red color has to be removed, and it will be also having a green and blue. So for the third it will be red, green and blue itself, that it is not the adjacent of 1. So let us come into the third iteration. So second iteration, in second iteration what is happening? So 1 will be placed with red only. So for the second one, that is for the second node, I will be using green color. So for the second node, I am using green color. So if I use green color here, what will happen? So 2 is adjacent to the 3 and 2 is adjacent to 1, which is already colored, so no problem for 1, and 2 is adjacent to 3 and 2 is also adjacent to 4. So for the 4 and the 3, it should not have the color green, right? So for 3, it should not have the color green. So what are the colors left with 3? It is only R and B. And what is the color left with 4? For here 2 G is already placed, and here what is the color left? So blue. So if 2 has green color, so 4 should definitely have the blue color. Okay, so that is what we have done. So coming to the third iteration, so first one is having the red color and second one is having the green color, and third one we have to check. So third one has the two possibilities, that for example, if you use red color, what will happen? If you use blue color, what will happen? So let us start with blue color. So for the third one, I have placed blue. So what are the adjacent to 3? So 3 is adjacent to 2. So 2 has green color, so no problem. But coming to 4, so 4 has blue color. So there is a problem occurred. So why this problem occurred? So we have to, so if we have problem occurred, so now we should backtrack. So you should backtrack, or we have to find the another alternative of the node. So we also have the another alternative, that is red one. So in case of B, we have to place the red one, red color. So in place of B, so if there is a no alternative and we have add an occur, I will explain by next step what we have to do. So now coming to, so there is an alternative, right? So now we have to place the red color, and for the, so we have placed red. So is there any effect of other nodes? So for 3, so 2 it has G, and for 3 it has B, that is blue color. So there is no problem, and G can be having blue color. So in the third iteration itself, we have completed our graph, that 1 has red color and G has 2 green color, and 3 has red color and B has 4 color. So this is how graph coloring will be done in CSF using backtracking in graph coloring. You know, for example, in case this graph doesn't have this R value, that is graph R, so what will happen? So B is the thing. So where this B has occurred, so this B has came because of we have assigned B here. So we have to backtrack. So here no problem, then here 4 has given B. So now we have to change the B value here. So we have to, if we want to change the B value here, so we want to change the 2 value, because from the 2 itself we have changed the value. So in case if 2 is given B, that is blue color. So 2 is given blue color. So what will be that? So 2, if it given blue, so what is the remaining term here? Remaining blue is given. So 2 is adjacent to 3 and 2 is adjacent to 4, right? So for green, it will be only having red and green colors, right? So red and green colors will be for 4. Red color should not be used because it is there, and 2 is already used blue color. So only color we have to use is the G color. So this is how we will be doing. So this one is the correct step, or this one is the correct step. So based on our assumptions and the backtracking techniques, we will be using all those things. Okay, now what we have seen, so G, so 3 is only having a RG. So in third iteration, so 1 will be having a red and 2 will be having a blue color. We have changed it, right? And for the 3, so 4 is having green color. And for third node, we have to check whether to give a red color or green color. So green is already present and blue is already present. What is the next color we can give? We can only give the red color, right? So that's why we should use red color in the third portions. And for the B, it is G color. So this is how we will be doing. If so, in case any error has occurred, we have to traverse back, or in case if there is no error, so we have to continue them. So this is the examples of constraint satisfaction problem. Let me just recap what we have learned so far. So I have explained all these steps, right? What is constraint satisfaction problem, etc. Then later we have dealt with the graph coloring example. So we have in exam they will be providing with the domains as well as the constraints. We have to find variable domain constraints and solution for that. So after that we have seen the Sudoku, that it is a 9 into 3 cross 3 matrix. So there will be a 9 boxes of 3 into 3 matrices. Then in each row and column we have to not place the similar values. We have to place another value so that the table will be filled. So then later we have seen the cryptarithmetic puzzle. Cryptarithmetic puzzle is nothing but the mathematical representation of numbers. Instead of numbers we will be using the alphabets. So we have seen the one example, as well as we have solved one logical reasoning question. Then we have seen the graph constraint satisfaction problem using backtracking with respect to graph coloring. So these are steps involved. So that's all about video. In case in exam if they ask write about constraint satisfaction problem, so note each and every step from start to end, explaining each and every step. So in exam just write any one of the example, it will be fine enough. So I will explain in deeply. So that's all about in this video. Thank you. Hope you like the video.